Okay, good morning, good afternoon, or good evening, depending on what time you are tuning in to watch this revision lecture. My name is Andrew Watson. I'm the founder of Project ATAR, a new venture designed to help VCE students, kicking off in 2026. But we're a little bit ahead of schedule, so we're going to release some material for math methods at the back end of 2025. And the first of those releases is this revision lecture on the statistics part of the math methods course. So without further ado, I'm going to flick across to the material and we'll get started. Okay, so what you should be seeing on the screen there is an overview of what's covered in this lecture. We are looking at the dot points from the study design. So really important we go back to VCAR's official reference for the material, and that is area of study 4, covering data analysis, probability, and statistics. The study design itself can be a little bit jargonistic, a little bit word heavy. So I've broken down those 5 dot points into 6 particular areas that we're going to cover off in this lecture. And they are as follows: 17.1, population, samples and proportions, very much an introductory exercise covering the vocab and the key terms we need for this part of the course. 17.2 and 17.3, you're going to break this into 2 sections, but they're both about the distribution of the sample proportion p-hat. One for small populations, which deals with our tree diagram work or our combination work. And secondly, for large populations, which is a more accurate model, and we're going to use the binomial distribution for that particular part of the course. 17.4, we look at the formal formulas for the expected value, the mean, the variance, and the standard deviation of p-hat. 17.5 is a nice activity because we're going to circle back to look at the normal approximation. Obviously, normal is part of the probability part of the course as well. And then 17.6, we come up with confidence intervals, and we get some tricky exam questions in this particular part of the subject. Now, down the bottom, you're probably looking at that diagram thinking this is a nice breakdown of study scores, and it is in fact a bell curve distribution. So all your study designs are based on a bell curve, so it's a normally distributed distribution. With a median of 30, you're probably well and truly familiar with that. What you may not know is they have a standard deviation of 7.6. So if we write that as the variance, 7.6 squared. Now that gives us a nice breakdown of what percentage of students score above and below a particular study score based on that distribution. And that's how these notes and this lecture is going to be targeted as well. So we have 25% of questions, roughly, which are rated 1 star. So when you see each of our examples, 25% of questions are really foundation building questions. They're targeting those students that are just developing their knowledge, or they're introducing some key ideas that we need for the more difficult questions. 50% of students and questions will be in this middle band, and that covers off those study scores between about 25 and 35. And obviously, once we get through those, we're building some really concrete base in terms of developing our mathematics, and then we're pushing on towards the top end. So that top 25% of questions and students, we've rated a 3 star in terms of our examples. Now, if you're at this really pointy end, your 45 plus study scores in the top couple of percent, there's probably a little bit of this lecture that you can get some value from, but I would suggest most of your time is better off doing your trial exams and working on those more difficult questions. So this particular revision lecture may not be everything that you need at this stage of your preparation. So let's jump into the material. As I said, that's the 3 star rating we're going to use. The way my lectures would tend to work is I would be giving a set of blank notes for students to go through. With each of those examples, we would start with a little bit of an overview, the concepts, the key formulas in a summary box at the top. We would then move down to those particular examples, and we would fill in those blank versions as we go through the lecture. Because this is a pre-recorded video, I've actually put together a series of work solutions, which we'll go through just to expedite the process and make the best use of our time as we go through the next hour or so. So 17.1, as I said before, it's a very much an introductory activity in terms of building some of your knowledge for this part of the course. I'll just zoom in there for you guys. And it deals with some of the vocab that you're going to need. So population, the full set of individuals. Sample, the subset. Now, you've probably heard the word subset before, and we've got a symbol for subset, which is A is a subset of B. And we'll use that in our probability or our set theory. All right, so here the subset is, the sample is the subset of the population. Okay, so we could write that out using formal mathematics. Our population proportion, P. Okay, that's going to be a proportion of individuals in the entire population that possess the characteristic or the attribute that we're looking at. Now, it is a fixed value. We may or may not know that population parameter, but it is fixed. And that is one of the key ideas that comes through this part of the course. The sample proportion is not fixed. It is based on the particular finding in a sample. So if we have X successes or outcomes that possess that attribute, then our p-hat value is going to be X divided by our sample size, N. And that will vary from sample to sample. As you can see down the bottom here, it varies, but the larger the N value is going to make it less variable. And that's when we start to actually quantify it with things like the standard deviation and the variance. Also importantly here is p-hat is only ever an estimate of P. It may in fact be the true P. We don't know, or we may or may not know. Okay, so that's some of the introductory language and concepts we're going to deal with here. As we scroll down, we're seeing our first example. Now 17.1.1, it's a one-star question. It really is just conceptual building in terms of introducing these key ideas. So we'll whiz through this reasonably quickly. We've got a library with 1,800 members. 1,800 members, I need to be able to fix that. 1,800 members. Records show that 1,080 of those members borrowed at least one ebook. A random sample of 40 members is selected, and 22 of those members report borrowing at least one ebook. What is the size of the population? So we're looking at the overall set of information that we have. So 1,800 members, okay, that's our population size. The size of the sample, well, we can't probably survey all of those. So we've got a smaller sample, and that is a sample size of 40 members. Question C, what is the value of the population proportion P? So that is a fixed value. As I've said before, we may or may not know it. Here we do. We've got 1,800 members, and we know that 1,080 of those members have that characteristic, which is to borrow an ebook. Right? So we can find the proportion P, 1,080 divided by 1,800. We can leave that as a fraction, or we can decimalize it if we wish. Now D is our first sample. So we've actually sampled or surveyed 40 members, and 22 of them have that characteristic. So p-hat of that particular sample is that fraction, 22 over 40, which we could leave as a fraction, we could simplify, or we can decimalize to 0.55. Now you can see it's less than 0.6. So question F asks us, well, why is the expected value not the same? Why did we not get 0.6? Well, the fact is we didn't survey everybody, okay, which is those two tied together. We just took a sample of 22 out of our 40. Okay, so we'd expect to get some variation. Now we're reasonably close, 0.55 compared to 0.6. All right, but our key finding here, and probably the thing we need to stress, and I'm probably harping the point a little bit, is that p-hat is random, and it varies from sample to sample. So a single sample proportion, like the 0.55, need not equal its expectation. All right, it may, but it may not. Okay, so that's the key idea out of 7.1. All right, hopefully that's all good in terms of an introductory activity, and we'll keep moving through to 17.2. 17.2, we've got the distribution of capital p-hat for small populations. Now, we'll just touch on the difference between the little p-hat and the big p-hat. So if we head down here, we use p-hat for the random variable. So when we're talking about the idea of that random variable, it's a capital p-hat. If we have a particular value, we've actually realized we've taken some numbers like we did in the first example, and we've actually come up with a number, then that's going to be little p-hat. And it matches the same idea that you would have had from the probability part of the course, where we have capital X being the random variable and little x being that particular value. Okay, so the ideas there are linked in terms of the use of the capital letters. So what else have we got in this section here? We've got the idea that we need to find the probability, and we've got a step-by-step process. So what we're looking for here is we want to get out of sample proportions and back into real outcomes. So my first dot point here is to turn the proportion into a count. So rather than dealing with tricky fractions or decimals that don't really have concrete meaning to us, we're going to take our sample size n and the particular value of p hat we want to work with. We're going to work out what that actually means. We're going to put it back into context. So here you're seeing we've got, if the sample size is 3 and p hat is 1/3, what does that actually mean? We've sampled 3 people. We want to find out what p hat is 1/3. What does that mean? Oh, well, that means that 1 out of those 3 people. So x is going to be 1. All right, and that's what we're looking for. We're looking to get out of p hat and into x. And that makes our life a whole lot easier. How are we going to do that? We are going to try and construct tree diagrams. I just need to switch this off, stay on the call. And they're going to be with no replacement. And you're going to see why that is for small populations in a minute. We're going to have a sample size that's quite small. And then it's your probability work. So adding or identifying relevant pathways in the tree diagram and adding those to get the total value. All right, so let's jump down and have a go at 17.2.1. We've got a bag containing 6 blue balls and 4 red balls. So straight away we're thinking the population is 10 balls. Okay, so it's a small population. So if we sample, and what we're going to do here is we're going to take a sample size of 3 balls. Okay, so we've got a sample size of 3 balls. It's going to be modeled by probability without replacement, because as soon as we take 1 ball out, we're going to really impact the probability. Okay, so this whole idea of a small population, meaning if we think we are going to impact the probability by taking 1 ball, 2 balls, 3 balls, or a sample, right, then it's going to be probability without replacement. Now that requires either some combination work, which we'll touch on in a minute, or our tree diagrams. And I think for most students, the tree diagrams is probably the best approach because you can really visualize it and link it back to the previous part of the course. So we want to find the probability that the sample proportion, okay, so remember that's p hat, sample proportion, is equal to 1/3. So we set up a tree diagram. We've got B is blue balls, R is red balls. Now what do we want? For p hat to be 1/3, we talked about this before, we need exactly 1 blue ball. So let's get out of p hats and work in the world of real things, X, capital X. So this is our first step. We're going to switch from the probability that p hat is 1/3. We're going to make that the probability that X, the number of blue balls, is 1. Now, how would we do that? We'd actually go back to identifying the branches in our tree diagram. So we need to look for any branch that has exactly 1 blue ball. So we've got our top branch, 1 blue ball and 2 red balls. We've got a branch down here that's got 1 red ball, 1 blue ball, and 1 red ball. And finally, we've got the branch down here. So we've got 3 branches that give me exactly 1 blue ball. Now, because it's probability without replacement, these probabilities on the branches change. So you can see we've started with 6 out of 10 blue balls. Okay, but by the time we draw a blue ball, we're down to 5 out of 9 blue balls to the second branch. But there's still 4 blue balls out of 9. Sorry, 4. Should start that again. 4 red balls out of 9 remaining. Okay, so it's that old tree diagram work from the middle school mathematics that you've seen before where you change the probabilities on the branches. Now, what you'll note when I construct that is leave your probabilities as fractions. Well, they're always fractions, but don't simplify them. You actually want to see what's happened here. So don't take 3 or don't take 6/10 and convert it to 3/5. All right, leave that to the end to do any sort of conversions. Because what you're going to see here is the lovely symmetry that comes through these tree diagrams. So these 3 options, a blue, red, red, a red, blue, red, or a red, red, blue, they're all equally likely. And they've all got this probability by multiplying those 3 branches. It doesn't really matter the order. And that's going to give us a nice shortcut in a minute. Because that order doesn't really matter, it's actually 3 lots of this quantity. All right, so we've got 3 of these added together, which gives us 216 on 720, which we can then simplify towards the end. Now, what you will notice, as I've said before, is those probabilities were all the same. Now, that may be a time-consuming method. It's a bit of a fail-proof method in terms of setting up the tree diagram, but you might like to look at some ideas with your combination works. Now, some schools do lots of work on combinations, others do very, very little. So depending on what background you have, this may or may not be familiar to you. So our alternative solution to this is to think about, well, how many ways can we do this? Out of 10 balls, how many different ways can we extract 3, and what sort of combinations can we get? So we think about a combination work, and this is our shorthand way of writing 10C3. There are 120 ways of picking 3 balls from 10 balls. Okay, that's our combination, 10C3. That gives us 120 particular samples. Now, of those 120, what do we actually want? We want 1 blue ball and 2 red balls. So how do we construct 1 blue ball and 2 red balls? Well, 1 blue ball, there's 6 to choose from. So the number of ways, the number of combinations there would be 6C1. So there are 6 combinations of blue balls. There's 6 to choose from. We've only got 1 blue ball, and there were 6 different ones. It's a fairly intuitive way of thinking about the number of options there. Maybe less intuitive is if we want 2 red balls from 4. Remember, our sample had 4. Sorry, our population had 4. Then there are 4C2, which also gives us 6. Now, because we need both of those things to occur, we need to multiply them together. Okay, so that gives us a number of combinations that are successful. All right, this is our little x. The number of successful combinations is 36 out of a total of 120. So you can bypass all the tree diagram work if you're confident with that idea of expressing the combinations and using those to actually construct the number of valid combinations that you're going to use. Okay, so that's another piece of, or another tool that you can grab from your toolbox. Okay, 17.2.2, we've got the same construct for the question. We've got 6 blue balls and 4 red balls. Okay, and we're taking a sample size of 3. So nothing has changed here. All we're after here is a more detailed breakdown of the distribution. So we have already looked at this particular category here. So we looked at the probability of 1/3. That was all the work in 17.2.1, right? So you could see the detail and the way that is built up. This is a nice practice question to fill in the remaining gaps. So the blank document of these has you filling in the remaining gaps of these. So you can follow exactly the same process to find p hat is 2/3, which equals 2 balls, okay? Or p hat is 1, which means all the balls would be blue. This is the blue, blue, blue combination. So it's really good practice for developing your combinations, drawing your tree diagrams, but a little bit time consuming. So we'd want to be able to jump to the CAS as well. So each of those calculations we did before, okay, get replicated here. And I've used K as 0, K as 1, K as 2, K as 3. And we can jump over to a CAS calculator and do that reasonably quickly. So just to recap where we'd get those skills from, if we can pull across to a CAS document. All right, we want to actually find out these particular values. Let's just shrink that down a little bit. Okay, we want to find the NCR values. So your NCR, you can either type it on the screen, NCR, or you can construct it through, we'll go for the fraction, and we're going for menu, probability, combinations. So menu, 5, 3, and that gives you your NCR. So following that first example, 6, 0, that's the number of ways we'd get no blue balls, times NCR 4, 3, that's 3 red balls. Okay, that top line is no blue balls, 3 red balls. How many balls were there, or how many samples were there? 120. Where's that from? NCR 10, 3. Okay, so you can see the construction there. That gives us 1 in 30. What does that mean? That's this 1 in 30 over here. All right, there is a 1 in 30 probability that p hat will equal to 0. There'll be no blue balls. All right, and you can go back to your tree diagram and you can see that branch as well. All right, so that sets you up for this style of question, and then you're going to get more variations on it. So these questions tend to start with probably a show that question, something to get your teeth into, and then you can start to use your probabilities. So we want, in question B, we want to find the probability that p hat is greater than 0.25. Well, it's a little bit meaningless, that 0.25, because it doesn't really exist as an outcome. But 0.25 is thinking about, well, what have we got in here? We've got, that's our breakdown. All right, so 1/3, I'll just take these off. 1/3 is 0.33, and there is our 0.25 marker. All right, so we're really looking at, well, what's the probability it's greater than a quarter? Well, all these are greater than a quarter. So it's the sum of these probabilities. We're going to add those together to get the total probability, okay, that we are going to be greater than 0.25. So this is like we're going to add the probability that X equals 1. 1 blue ball, 2 blue balls, or 3 blue balls. Okay, combine those together and it shouldn't surprise you that it's a number fairly close to 1. Now, again, you're starting to think, well, hopefully you're starting to think, that's a bit time consuming because I've got a few more skills. I can recognize this is going to be 1 minus our complementary probability, 1 minus the probability that p hat equals 0, or 1 minus the probability that x equals to 0. Okay, and that's a short way to get through that. But it's a nice way of thinking about the sum and combining those probabilities. The final part is going to be a conditional part, and you should be aware that that's the way these questions tend to be structured. We now want to ask ourselves the question, well, I've got P, what's the probability that P hat is 1/3, given that the probability is greater than 0.25. Now, most questions, you've already got this information. You've got to tie it together somehow, but don't go redoing these calculations because we've got everything we need. When you think about how that visually looks, again, with our diagram up the top here, we're looking at conditional probability. You are told in the question that it is greater than 0.25. Well, what that means is we are looking at this particular groups of probabilities. Okay, so you've isolated that particular part of the diagram. This 1/30th, it's no longer included in the subset. So from that group that is included, well, what's the proportion that it is our particular category? So that 36 on 120 is the probability it's 1/3, and we want to compare that to the overall, right? So that's what this calculation is doing. We go back to formulas, but it is what fraction is 36 on 120 compared to that total, right? So you're extracting the subset as well. And that calculation is going to look like this because we have our two parts already. So in the first part, we calculated 36 on 120, and the remaining part, we had 116 on 120, using that part there. And the reason I kept it with this is because when we have a fraction on a fraction, and these are the same, they will cancel out. Bottom will cancel with bottom. All right, if you're not convinced about that, any of your fraction work, we can treat it like a separate division, and we can extract it, and we can have 36 on 120, keep, change, flip, and you'll see that's where it's cancelling. All right, so fractions are a little bit hazy for you. Write them out as best you can and go through the process of keep, change, flip, and fractions in fractions become a little bit simpler for you. Okay, we've just scrolled down here. We are looking at 17.5 distributions of p hat. Now, I've just come across there, but you can see the heading under there. We've got the idea of large populations. Now, we want to find the probability of sample proportions in a large population. So how large is large? Well, it's not for you to make the decision in the exam. The exam will be fairly clear in terms of whether it's large or whether it's not. Okay, they will be really, really specific in terms of what's required. But if it is a large population, then taking 1 or 2 or 3 out of that population will not impact the probabilities. So if we go back to that original tree diagram, we had branches that were changing 6/10 to 4/9. That's significant. All right, there's a bit of a change there, or sorry, to 5/9. There's a bit of a change there. But if we had 1,000 or 10,000 or 100,000, then taking 1 out of that really doesn't impact the probability. It still changes it slightly, but it's not going to affect our mathematics to any degree. So if we come down here now, if that's the case, we can start looking at this like a binomial distribution. So large populations approximate sampling with replacement. And with replacement enables us to do our binomial calculations. That's why we've got this lovely overlap to the previous part of the course. So really what we're looking for here, if we want to find the population or the probability that p hat equals p hat, little p hat, then let's take it back to x, and then we can use our binomial formula or our CAS calculator in most cases. So let's get to the examples. We've got 17.3. We've got a very large database. So there's our clue, our very large database. And exam questions will be even more specific. We've got a large database so we can use our binomial distribution. And we have information about the population. Let's go back to my red. We have information about the population. We've got P equals to 0.25. Okay, so extract that. That's the first thing we need to look at. And then from there, we actually want to do the similar sort of calculation to before. We want to find the probability that P hat equals to 0.6. And that's going to be the probability that X equals to 3. So this line's really important to us. We stressed it before. Get away from P hats and get into X as quickly as you can with this style of question. Because then you can start thinking about, well, what do those numbers actually mean? I want 3 movies out of 5 movies. Okay, 3 movies out of 5 movies. Well, that enables me to use the binomial distribution. So we've got either a by hand calculation. Okay, so we've got 5C3 times 0.25 to the 3, number of successes, 1 minus number of fails is your 0.25. Okay, so you might be more familiar with 5C3. We've got 0.25 cubed, and then 1 minus 0.25. It's like our Q or our fail squared. So we can either do that manually, or we can go to the binomial PDF. All right, so you've seen the difference there, binomial PDF and CDF. If we flip across quickly to our CAS menu, probability, distributions, binomial PDF. Okay, binomial PDF, we've got 5 trials. We want to find a single value. Probability of success is 0.25. And we want to find 3 successes. And there's our 0.08, rounded to 3 decimal places, 0.088. All right, similar setup we've got now. We want to find the probability that P hat is greater than 0.6. Take it back to the real concrete meaning. It's about movies. How many movies? Greater than 0.6. Well, that's X is greater than 3. Okay, 3 times 5. So we've got 3 plus 4 plus 5. Okay, this time it's a binomial CDF. Okay, similar part of the CAS we've written before, rounding to 3 decimal places, 0.104. Part C, again, look for the last part to be a conditional probability. We know we've got greater than 0.6. Okay, and we want to find the probability that P hat is exactly 0.3. Okay, so that's the whole idea before. We've got the various parts to it. What does that mean if we draw it together? It means, well, X has to be 3, but we're only considering the values greater than or equal to 3. So we have those 2 parts from up here, 0.6, and here, greater than or equal to 0.6. One thing I do want to stress here is the rounding. So this question asks us to round to 3 decimal places. Now you must ensure that you've put in non-rounded values here. So there's my full calculation on the screen. All right, so we get a final answer of 0.849. I just want to show you what happens if you use rounded values. So if I've actually got these questions correct, all right, and then I jump across and say, this is going well for me. I now need to do a division, and I take those 2 values. So it'll be 0.088 from part A divided by 0.104 from part B, 0.846. All right, now that's different to our correct answer, which is 0.849. Because we've rounded too early, we've introduced this error. So make sure if you're going to write these out, if you're going to do it by hand, you actually have a few more decimal places. So 0.088, I've gone off the screen, but we should have a whole lot more decimal places we can actually use to get those exact values. So please be cautious of that, introducing those rounding errors. I've got to say, most exam questions are set up so they avoid that, but it's something you should always be very cautious of as well. Okay, 17.4, the expected value, the mean, the variance, the standard deviation of P hat. So a lot of these formulas are on your formula sheet, and this one we've touched on before. which is the expected value. We've now got the variance and we've got the standard deviation. Okay, so these formulas are really similar to the ones for X. However, the difference is going to be the placement of N. We'll talk briefly about the connection here. As we were converting from p hat to X, we were multiplying by an N value. Okay, so you're seeing that the expected value of p hat was P, the expected value of X, multiply the two together, NP. Difference being your variance calculation, your standard deviation calculation, they vary by a factor of N squared. It's to do with the actual calculation process of a variance. We're talking about difference of squared values. So what you're seeing here is to get from this value to this value, we've got a multiplication by N squared. That's not something you need to remember. You do need to remember there are a difference between those two formulas and be really cautious of the placement of N. All right, so are you after the variance or standard deviation of the sample proportion, or are you after the variation of the actual score X? All right, so be really careful with that. Again, what we've been doing is to convert to X. All right, so get out of the world of p hat and into the more concrete contextual value of X, and then we can use our binomial. 17.4.1, just a 1-star rating here. So this is just going to really develop our skill base in terms of what we want. We've got a large population. We've got a chance of success. P is 0.3. Okay, it's a known factor. Simple random sample of 50 is taken, and we want to find out those particular things. All right, so we can plug those in the formula. E of p hat is just P, 0.3. Variance, we can plug that in, and the standard deviation is just the square root. What you might like to do, and probably not an area of the course that is an urgent need for it, you might like to create some of these formulas ready-made on your CAS calculator. So what you're seeing there is just an idea that you can toy with other parts of the course as well in terms of building up a formula and having it ready to go as well. So we're very much used to the idea of defining a function as fx, but you can actually define a calculation or a formula. So if we want the variance formula, it's got two inputs. So the variance is going to be N and P. We need to give the variance formula two things, N and P. Now we can store that, or we can set it equal to the actual formula, which is going to be P times 1 minus P divided by N. All right, and we've got a formula there that's ready to go. Now it is just the variance of p hat, so maybe we should have defined a little bit better than just rather than var. Okay, so we could actually go back and say, well, we've got two variance formulas. We might want to put this one as a var with a p, or even write it as var p hat. Up to you. You can call it what you want. It's a formula that you can use. So if we want to find the variance, var p hat, and then we give it the two inputs. Any question that gives us n and p, we've got an n value of 50 and a p value of 0.3, and it'll calculate it straight away. So you might want some of those set up. As I said, this part of the course, maybe not, but it's worth thinking about in terms of how you can get more functionality out of your CAS with fairly low degree of input in terms of what you're actually programming it to do. Right, but that has distracted me a little bit. So let's get back to 17.4.2. We want the sample sizes of 100 taken from a large population. Standard deviation is. Right, so this is a fairly typical sort of question. We're really targeting that middle band, those 2 stars, that middle 50%. We've got a formula on your formula sheet, standard deviation, and it's got two inputs, P and N, and you've been given one of them, you've been given N, and you've got to obviously find P. All right, so we're going to plug in our values. Now, if it's CAS active, all right, by all means, straight away, we can jump in and do a solve. Now, because P has to be a proportion, it is between 0 and 1, it doesn't impact the solving of this question here. But if you want to do a restriction outside the solve brackets, given then. Okay, so given that P has to be between 0 and 1, what is going to be the solution for P? By hand, I chose this one nicely because it gives you a little practice with a perfect square. We've got P, sorry, when we square both sides, we're going to square this side of the equation. Okay, which gives us 0.25 after we multiply by 100. That sets us up with a quadratic. Quadratics set equal to 0. You may recognize it from that form there. If you're not comfortable with that form there, you could multiply everything through by 4. So you could see, well, I don't like 0.25. Let's go for 4p squared minus 4p plus 1 equals 0. And then maybe from there you recognize that as 2p minus 1, 2p minus 1 equals 0, or p equals to 0.5. Okay, so either way, but be prepared for the examiners to test you on other parts of the course, solving a quadratic, setting up an equation, working with square roots in this part of the course. Scrolling down, 17.4.3. We've got a 3-star, so there's something a little more challenging here in this, and I think it's on the last part. We've got 40% of commuters in a city take public transport. Well, that's a fact. It's stated to us. That's going to be our p-value. 40%, 0.4. Okay, your conversion with your percentages. A random sample of 30 is chosen. Looks like I've mistyped that there. So that should be 30 is chosen. And we've got p hat as 0.4. So straight away we're thinking 30 is great. What are we expecting to get there? P hat is going to give you a value of 12. So 0.4 times 30. That's our x value, because we are after the probability the sample proportion equals the population proportion. Right, so what does that mean to us? We've got p hat equals 0.4. How likely is that from our sample we get exactly 12? I got a little bit ahead of myself with explanation there, but that's what we're thinking about. How likely is it? Not impossible, all right? Not certain, but somewhere in between. So we've got our combination work. It's a large population. We're talking about commuters in a city. Okay, it's not going to be 10, it's going to be thousands. And we're looking at our work, which we've got NCR. We've got 30 C12 times 0.4 to the 12. That's how many we want. 1 minus 0.4. That's our failures, people that don't take public transport. And out of a sample size of 30, well, these two have to add to 30. Okay, so 12 do, plus 18 don't. That's our breakdown. Okay, run it through your CAS. It's a PDF calculation after a single value that exactly 12 do. And as I said before, not impossible, not certain. A number like 0.147, 14%, 14.7% sounds like a feasible answer. We're good to go. Find the probability the sample proportion lies within 1 standard deviation of the population proportion. Okay, starting to get a little bit wordy here. Probability, so we want a calculation that the sample proportion 1, so lies within 1. Lies within 1. So it's like plus or minus 1 standard deviation. We can go 1 standard deviation above or 1 standard deviation below. And again, it's going to be like a probability calculation. So this time we're going to have some boundaries to set. First things first is we want to calculate the standard deviation. All right, so jump into your formula. Remember, the correct formula is the one with n on the bottom. So our standard deviation is going to give us 0.0894. That's the number we're going to work with. More challenging because we're in p-hat world, we're in fractions and proportions. So 1 standard deviation at either side. Well, remember we had 0.4, 40%, that's our p, that's the value we're using. So from that, add 1 standard deviation. So that's the plus 1. So add 1 of these to get the upper limit. Subtract 1 of those. All right, subtract 1 of those. And you can see the CAS shot over here. And you'll get the lower limit. Now, that's as much as we need to do in p-hat. Then we can get back into x values. So convert those back to the actual count, back to the actual outcome. And you've got n, so sample size of 30. Multiply them back up, and it actually gives you some values to work with. Now, they're decimal values, so it can be a little bit confronting to start with, saying, what does 9.3 commuters actually mean? Well, we're not interested in that. We want to be between these two values. Okay, so in between those two values means, well, any integer number. Commuters have to be whole numbers of people. All right, so 10 to 14. We're not rounding down. All right, we're not rounding up. We're rounding in. We're rounding into our interval. All right, so 10 to 14. That's what we're looking for. 10, 11, 12, 13, or 14. They are the number of commuters between 1 standard deviation below, and 1 standard deviation above. All right, so now we're satisfied with that. We can use binomial CDF. All right, 30.4, 10 to 14, add them together, or CDF to combine them, and round correctly, 0.648. It looks reasonably straightforward, but it's a 3-star question. A lot of students, as soon as they start to see those decimals, will lose a bit of meaning in terms of what they're after there. We'll also find, when we mark it, we'll have a lot of students round these values up. All right, they won't interpret that last stage correctly, so be cautious there. Now, given that, okay, last part again, following the same theme, given that, conditional, it is within 1 standard deviation. So you're looking back to, we know this value, find the probability it overestimates. All right, so unpack, what does this mean? Overestimating. We're taking a sample. We know the population proportion was 0.4. Well, of all those samples that we could take, what's the likelihood that we are more than 0.4? Okay, so that's what we're looking for here. We know it's between 10 and 14. And overestimation, there's our 0.4 times 30. 12 is our expected value. We expect to get 12. Anything more would be an overestimation, not including 12. Okay, so x is greater than 12 is our overestimation. 12 is the expected value. Right, so from there, you need to pick up your conditional work. A intersection B, how do these things combine? X is greater than 12 and X is between that. Now, if you're a little hazy with how to put those together, I would suggest a little number line and draw out those values. So you've got 9, 10, 11, 12, 13, 14, 15. That's as far as we need to go. We know we have to be between 10 and 14. All right, so that's those particular values. And we know we have to be greater than 12. Can probably change that highlighter. And we have to be greater than 12. All right, so that is that intersection. The yellow bit was the given then condition. And then within that subset, we saw it before with the table. It's that visualization process of thinking within a set, what is the subset that's required? Okay, so 13 to 14, given that, we've got between 10 and 14 inclusive. Okay, don't round off. This is before, don't round off. Keep your values till the very end. You can see this dot, dot, dot work. Okay, that means we're not rounding in our calculator. We're leaving the exact values as we go through. All right, really good question. If you're comfortable with that, as I said before, you're starting to head towards that top 25%. Well done. Normal approximation of p-hats. All right, so again, we're starting to think about large populations and what can happen. We're actually going to quantify when this is acceptable and when it's not, but we're thinking about the ideas of our normal and that bell curve shape, which we touched on with study scores at the start of the lecture. We've got a sample size is large and p is not too close to 0 and 1. Well, we might as well quantify it now. This approximation is generally appropriate, and depending on different literature you read, it may be 5, it may be 10. It's not going to be assessed, or if it is, they will tell you the criteria. But if it's large enough, just imagine it is. You're told it's large enough, then we can approximate it to be normal. What does that mean? That's a whole mouthful. It says, yep, okay, if you tell me it's normal, it's normal. But what we're looking for here is, I'll probably best show it with this simulation. If we know the population proportion is 0.48, and we're going to take a sample of 50. If I take one sample, I get a particular number. I take a second sample, I might get a particular number that might be different. It might be the same. If I start to plot those, you can see a distribution start to fall. So let's say my first value, I took 50 and I got, let's say it's 0.5. Let's say it's 0.5 exactly. So my first sample, I had X was 25 and I have N is 50. So my sample proportion, P hat, was 25 out of 50 is 0.5. Whatever the characteristic might be, 0.5. So I can plot that dot. That is one sample. It may or may not be close to P. We don't know. It's just a sample. Now, if I take another sample, this 25 may change. It may be 24. It may be 25 again. It may be a different number. But that generates different sample proportions. And then if we start to plot those, here is 10 of them plotted. Okay, and you can start to see there's some sort of pattern starting to develop. They're all starting to cluster somewhere towards this particular value. And that's no surprise because P is 0.48. All right, we know that. So we should probably expect, knowing that, they're going to start to middle out around about that value. Now, just by coincidence, when I ran this simulation, we had two values that were exactly 0.48. All right, these two values here. But we've talked in our examples previously, that's only certain likelihood. It's the most likely outcome, but it's certainly not certain and it's certainly not impossible. It's somewhere in between. We can calculate that. Now we're starting to find we've got a distribution that's starting to fall away. Now, if you increase your samples, say I take 200 samples, same parameters, 50 is the sample size and 0.48, we would find more and more of them hit exactly 0.48. Okay, that's logical. More and more samples will start to hit that 0.48. What you'll also find, however, is they'll start to fall away and you'll start to get this lovely shape, which is going to approximate our bell curve. We don't expect to find too many values out here. That's going to be more than 2, 3, 4 standard deviations away from the mean. And we've just looked at a calculation about standard deviation and been able to quantify that. So that's the theory, and hopefully that ties together what you've done with normal approximation earlier in the course. How is it going to unfold in terms of what's being asked? We've got 17.5.1, 2-star question. So again, none of this is going to be particularly easy. We're told 55% of a population. So we do know P. All right, so 55% is looking to me like P. There it is. Using the normal approximation. Now you will be told, all right, and you can't use it unless you are told. You'll be told to use the normal approximation and that within a sample size of 180, so it's a big sample, so it should be okay to use, more than 60% use that service. So unpacking what we've got an expected value. So you might see this as E of P hat. It's the same as the mean, it's the same as P, it's that 0.55. It's that starting position. We know that about the population. From there, we've actually now got a formula we can use for the standard deviation. Remember, it's the one with N on the bottom. Right, so this is going to be the standard deviation. You can write it out, standard deviation of P hat. It's how do they fall? We've got this idea that they're going to be distributed according to a particular rule, and that is our rule. So we'll calculate that value. That's our standard deviation for P hat. This is our mean for P hat. And we know a normal, we started the lecture with this, we're going to call it Y. A normal distribution is written as the mean followed by the variance. That's the way we describe that distribution. So here we've got N is 0.55, and you can see here I've just used the value before it went into the square root. That's our variance, or our standard deviation squared. That gives us the ability to use our normal CDF. So what we're looking for here is we know information about that approximate curve, not one of my better curves, and we know the median is 0.55, and of all these dots, so remember these are all going to be just dots of sample proportions, what's the probability we are greater than 0.6? Greater than 0.6. So we're up here. Okay, and that's where we now go into our normal CDF calculation on the CAS. So just to recap there, I can flick across. We will have our normal CDF, so menu, probability, distributions, up the top, normal CDF. We're after the top bit, so it's from 0.6 up to infinity, which is under the equal symbol, or pi symbol, I should say. Our mean was 0.55, and our standard deviation was the square root of 0.001375. Okay, and that gives us our value of 0.0888 rounded to 4 decimal places. All right, so it's a nice recap of your normal probability, but it's about your sample proportion. So yeah, just keep thinking about that diagram I showed you before, where this is our dots. This is our actual values that you would take from a lot of samples. Increase the sample, it starts to get that nice sort of bell curve shape. So there's our probability that it is greater than 0.6. Okay. Final example we have. This is an interesting one because it's a little more realistic in terms of why we would use samples or when we would use samples. So in a large city, 62% of residents support a new transit plan. So perhaps at a census, everyone was polled. We know the population, and we know 62% of residents support something. Now, pollsters, people that track things and trends across cities, would be interested in seeing if that changes over time. So once they know it's 62%, that's fine. That's a point in time. Well, does that change? And they would conduct some follow-up samples. So pollsters may flag a result, as in that may alert them to something has changed if the sample proportion is unusually high compared to the population proportion. So say they went in and they surveyed a group of 100 people, which is what we're doing, and all 100 people opposed that plan or were then in support of it. Something may have changed. So that's what we're saying with flagging a particular result. So we need to show the normal approximation for p hat is appropriate. Now, this is just one that I've used to practice that idea that we need to understand that it's not always appropriate. As I said, exam-wise, you'll be told whether it is or is not. And that is to say, well, have we got enough people there? Is our sample size and our population proportion okay? And these are the two formulas we're going to introduce. So NP or NQ, they're both large numbers. They're both greater than 5 or 10 or whatever the threshold might be. So yes, it's okay. So we're going to go ahead and use that. Now, we've got the normal approximation to find a proportion cutoff value C, so that only the top 10% of sample proportions are flagged. So as I said before, if 100 out of 100, it would raise concerns. But what's our cutoff mark? 90, 80? What are we thinking in terms of flagging an unusual result? And that's going to be categorized by, well, only the top 10% would be triggered as something unusual. So where do we fall with that? Well, we're going to need the statistics. So we're going to need the mean, which is the same as P, that's 62%, which we're given in the question, 0.62. We are going to need the standard deviation. So regardless of whether you can do this question or not, at least show that you understand the part of the course you're in and get these particular values. It may or may not be the method mark for this question, right? And then we'll start to apply them. Once you've got those values, all right, you're thinking to yourself, well, I understand I'm dealing in the world of normal, so write out that distribution. Just that writing of that distribution can often be the method mark. It's considered mathematical working for this style of question. Okay. Now we need the 90th percentile. We don't do a lot of work on percentiles, but what that means is we're talking about the top 10% of results. So the area here is 0.10, not the number underneath, the area, the probability, which means this probability here is going to be 90%. Okay, so we want the values to be less than that. So that requires us to do our inverse norm. Okay, same part of the CAS, but this time it's an inverse norm to work backwards to actually find that value of C. Now, when we use the inverse norm, it is always from the left-hand side. So it's always this particular area up to a value. So even though 10% might be the trigger point, you need to use the less than value, highlight it there for you, which is the 0.9 that goes into our CAS. All right, so I won't flip across to the CAS. You can practice that skill, but that is what we're looking for there. So that gives us a value. Now think to yourself, before you move on, what have I created there? What did that mean? Is it sensible? So we've got 0.62 being the people that, or the proportion of people that support the transit plan. We're interested in, is that changing? Is it getting too high all of a sudden? Or is it changing dramatically? And we worked out if it increases to 0.68, So we've got this increase. Okay, this is in the top 10%. All right, so that's what you're actually thinking to yourself. Now remember, with this, our decimals, our fractions, our proportions don't have as much meaning as the actual numbers. So in question C, we're asked, well, what is the smallest number of supporters that would trigger that flag, that would actually get into this 0.68? So you're connecting those two bits of information. So same skill set here, N times C. We've got a proportion, C. I know it's written as C, but it's still a proportion. If you multiply this by the number of people, multiply that by 100, you get 68.2. A lot of students will get there and then they'll round that down to 68. But if you round it down, you are coming in there. Okay, so you need to round it up to make sure you are in this particular area. All right, so just be careful of whether you round in or round out, and you consider the intervals that you're actually using. So we want it to trigger, we want it to be greater than the 10%, which means we've got to go up to 69. We've got to increase that to make sure we get into this particular area. All right, so hopefully you got some connection there with the idea of using the inverse norm in a different slide of, or different way the question is worded. A fair bit of overlap there with what's in the specialist course as well, for those doing special as well, looking at those tails in your special work. All right, last part. Hopefully you're still with us. So we've got confidence intervals for the population proportion. A lot of formulas here, a lot of stuff you probably need to unpack and get the concepts, because the mathematics is not going to be particularly hard. The concept is really challenging. Okay, so we've got our CAS to support us. The mathematics is not going to be hard. We're going to have solve and a whole lot of things we can use, but the ideas are really important. So I'll dwell on these for a bit. The first idea is that a lot of the questions we have done and we practice, they don't model reality because we are told the population parameter P. The reality of doing surveys and sampling is we do those samples because we don't know what P is. So the first idea we're going to start with here is, if we do a survey, we get a P hat value. Now, because we don't know what P is, okay, we don't actually know what P is, we're going to use that as the estimate. All right, so we're going to say, here's a sample. I took 1,000 people, 300 of them supported something, 0.3, let's use that as P, because we don't know what P is. It's our starting point. It's a point estimate. So from there, we can develop a confidence interval. And you can start to think about, well, that 0.3 I just spoke about before, how reliable is it? Is it a value that's worth using? We need to actually express or quantify whether that is a reliable value to use, or is it just made up and it's worthless? It's no point actually persevering with what I'm trying to do with my statistics. So our confidence interval is trying to quantify, well, from an estimate, how reliable is it going to be? And I'll introduce the formula and we'll unpack parts of the formula. First of all, it is an interval. It is between two things, okay? So we're going to have some sort of range and we're going to have particular values, and we have percentage confidence that we're within these particular values. So what the first idea is, these are always centered on P or P hat. It should be P hat, sorry. They're always centered on P hat. So that's the middle of our confidence interval. It was our 0.3 I talked about before. And from there, we go a certain distance to the left, like we did with the standard deviation example, and a certain distance to the right. How far? Well, how far is this bit of your formula? You can see it on the left and you can see it on the right. And it's got its own name. It is called the margin of error. And we give it the symbol M, capital M. And that dictates, as I said before, how far away from the center we have to go. And the center is a really key idea here. So from P hat, we're going to go left and we're going to go right to create our interval. That margin of error, which I highlighted before, is made of two parts. It is made of the standard error, which is really, and the mathematics is a little bit fuzzy here, it's called the standard error. The study design says you don't have to know that term because we're probably going to refer to it as the standard error or the standard deviation of P hat. I said, well, the mathematics gets a little fuzzy here, but standard error, standard deviation, it's going to mean the same thing for what we're dealing with in the methods course. And we have a formula for that. Okay, that's our standard deviation formula. We've used it a few times before in this lecture. So that's part of the margin of error. The other part of the margin of error consists of a multiplier, which really dictates how confident we want to be. So do we want to go 1 standard deviation, 2 standard deviations? Remember, this is just the standard deviation part. How many standard deviations? So that's what Z is. It's dictating, and those doing general maths know it as a Z score. It's dictating how many standard deviations we want to move away from the median. Now, the first thing we want to look at is, well, how do we find out what that Z score is? And I'll scroll down to this particular table. We've got a Z value. Remember, it's normally distributed, median of 0. It's our standard normal, variance of 1. So it's centered on 0. Now, we want to go a certain number of standard deviations away. If we convert that to p hat, that's going to be our margin of error. So we're going to move away. So how do we find that number? Now, there are some values you may know before. Again, those doing general maths may know, or even part of this course, the 68, 95, 99.7% rule. They correspond to 1, 2, or 3 standard deviations. There are some other values we're going to set here, which are confidence levels of 90, 95, and 99. They're going to correspond to particular Z values. And I'm going to show you in a minute how we find those. All right, but they are the common ones that are often used, so they're worth seeing in a table and actually presenting it. So if we know the Z value, lock it in. We can then find the margin of error, because the margin of error is just Z times the standard deviation. So you're breaking it down into parts. Once you know the margin of error, you can then find your confidence interval. All right, so you're going to move away from P or P hat. There's the same thing in this situation, right and left, to find your confidence interval. Lots of words, lots of concepts there. The diagrams are really important, but let's get into how we actually find one. So we want to find the Z value for a 68% confidence. Now, you should be ringing bells. What I said before is 68%. Isn't that just 1 standard deviation? Well, it is roughly, because it's only ever been an approximation rule. So how do we find that exactly? 68% confidence, 3 decimal places. Draw your bell curve. So this is the Z curve, normal, 0, 1 squared. All right, 68% meaning 68% in the middle. We want to go out a certain number of standard deviations either way. We think it's 1, but let's get it exact. So we would go to our CAS, and remember, it's always with the inverse norm. It's the area less than. All right, so if you put 0.16, it's bottom calculation, 0.16 in your CAS, you'll get that Z value of minus 0.994. If you put in 0.84, which is 16 plus 68, all right, you'll get 0.994. So that's our Z value from a 68% confidence interval. It confirms what we know about that approximation rule. So that's how you find your Z values. Now from there, let's go back to, well, how are we going to use that? So if I scroll down here, we've got a sample of 220 students. 128 say they prefer studying with music. Find the 95% confidence interval for the true proportion P, which we don't know. We've only got that sample, remember. So we're going to use P hat, 128 to 20. We make up our P value from P hat. Okay, that's what we've been doing, 0.5818. Let's then find the standard deviation, call it the standard error if you like. It's a formula with N on the bottom. It's on your formula sheet. Plug it in, you'll get standard error of 0.03328. They're the values we can use, and then we can start to think about, okay, this is a normal curve. I understand the idea of normals. Draw it out. Okay, and then you can start to think about, well, what do I actually want? We want a 95% confidence interval. Find the Z score. All right, you can either go back to the table, because I've got some common ones in there for you. So Z score of 0.196. All right, or you can find it yourself using those calculations. All right, so you'd find a z-score of 1.96 corresponding to that 95% confidence interval, and then you're going to plug it into find the margin of error. Z-score, margin of error, multiply those two together. It's the link. You're taking these two, multiply them together. That gives you the amount you're going to go plus and minus to find your confidence interval. So from here, your confidence interval is developed by p hat, subtract one lot of m, and p hat, add one lot of m. Right, that gives you your confidence interval to 4 decimal places. All very well if you have to show working or you've got to do it by hand. You want to do it straight away. You've got your CAS functionality, which has an inbuilt command, and we'll walk you through that. So it's menu 665, and you're looking to go menu 6, 6, 5. There are two that look pretty similar. So remember, it's 5 prop Z interval 1. All right, successes we know is 128. There were 220 students, and we want a 95% confidence interval. So 3 numbers to input, and you'll get all the values that you need that confirm your sort of by hand calculations. Now, if you look at exam percentages, less than 2/3 of students can do that in terms of inputting those 3 numbers into a CAS calculator. Okay, that's how much it drops away at this part of this pointy end of the course. But you're looking for confidence intervals there. You can see those values, 0.5166 up to 0.649, just get your rounding correct. Right, last thing touch on here is what does that mean in terms of interpreting? Look, unlikely to be really quizzed on this in an exam, but again, I think it really enhances your understanding if we just spend a minute just talking through those dot points. Can't stress enough that that p-value is fixed. All right, as I said, most questions we're told what it is. That doesn't model reality where we don't know. So it's going to be an unknown population value. The randomness, we've talked about random samples. We talked about the distribution. You saw it with the simulation as well. All samples, well, that's probably not quite true, but samples will be different. Okay, some may by coincidence be the same. Now, 95% confidence interval method is a method that in the long run hits the true P, because remember, we don't know what the true P is, about 95, that's that roughness, % of the time. So if we repeated that sampling, all right, so it's not about 95% confidence, it's about if we repeated that sampling 100 times, then we would expect 95% of those intervals would have P. So let's just unpack that a little bit more. After we have our data, it's fixed. So it's not right to say there is a 95% chance. So this top one here, this was the confidence interval I created. I don't know what P is. It may or may not be in that. If I did another sample, let's say I repeated this calculation and this time started again, I had 120. All right, if I repeated that, this time 120, I would get a different confidence interval with 2 values from a new sample. If I did this 100 times and I created 100 confidence intervals, we could say there's a 95% confidence interval produced by a method that succeeds 95% of the time. All right, so of these, this may or may not contain P. That's the key thing here. May or may not. You cannot say whether it does. We don't know. But of 100 of those, using the same process, the same values, 95% of them should contain P. 5% will miss. It's just the random nature of the sampling. As I said, unlikely to be examined, but I think it is worth just consolidating your concepts there in terms of what we are doing and why we are doing this. Right, last 2 questions. We've got 17.6.3. We've got a sample proportion, very classic type of exam question. This one's come up a fair bit in the last couple of years. We don't know P, but we've got P hat. Don't have a context here, but we've got a minimum sample size. So we don't know the sample size. But we want to reduce the margin of error. Now, this is a fairly common statistical measure. You want to have confidence in the work that you've been doing. So you want to reduce the margin of error. So that would generally mean sample more people. All right. So straight away, you should be starting to think, okay, well, as n increases, I talked about this right at the start, as n increases, we're going to become more confident. We should be reducing the margin of error. And mathematically, look where n is in your formulas. N is down the bottom there. If you increase n, and it's on the bottom of a fraction, you will decrease the margin of error. Okay, so that's what's happening here. Now, can we quantify it? We can absolutely, because we've got a formula. We've got the entire formula, or you've got that part of the formula that is margin of error. Remember, it's the Z part. All right, so first things first, 95% confidence interval. You want to convert to that Z value. Might be one you know, might be one you've got to find using inverse norm. So once you've got that Z value, you can set up that formula. Now, these are often asked by hand. They're often asked by hand, okay? So be careful of your arithmetic here, but you're going to be squaring both sides. So you can see here, we're going to reduce this down, bring this across, and then we square both sides. Okay, once we square both sides, we've got n on the bottom, and we'll cross multiply across. So just make sure you can do that by hand, because as I said, it may be a by hand, it may be a CAS question. Right, that gives us an n value of 1024.4. Again, you need to be able to interpret what that is, and that's why the concepts are so important here. So the concept is we want to have a margin of error no more than 0.03. So if you are thinking to yourself, if I have a higher n value, I will reduce the margin of error. I'll become more confident. Then once you get to this final step here, you should be starting to think, okay, well, to keep the margin of error below something, I would need to round up and survey more people. All right, 1,024 goes up to 1,025 to keep it within. Now it's presented in a couple of textbooks. I'm not a big fan of that formula. That is just rearranging what we've done through here. So there are formulas that are presented, and some people have them in the summary books that rearranges this margin of error form. I think I'd much rather you unpack the ideas rather than plugging it straight into that particular formula. But that will do the same thing if you can recognize the parts of that formula and plug them in as appropriate. Right, final question. 3 stars, and it's bordering on 2 to 3 stars, but the way I've presented it here, it's slightly easier than a version you might see, because I want you to see how this unfolds and the common point that the students sort of miss as they try and get to this level. So we've got a confidence interval. Now this time it's expressed as 0.42 plus or minus something. So it's almost all ready to go in a form that you like. This is a really common way, and you're going to see, particularly coming up to local, state elections, federal elections, you're going to see pollsters talking about whatever party had a 0.4 plus or minus a certain percentage, tolerance. This you might see as a confidence interval in a more traditional form. And that's what I want to dwell on here. This whole idea of taking a value in the middle, 0.42, adding, subtracting to get the interval. So if we subtract, you get 0.375 at the lower end, and add to get 0.47. If it is presented this way, and it often is, I want you to be confident, because a lot of students aren't getting it back into this form, right? Because a very simple question that students actually miss here is, from that confidence interval, what is P? What is P hat? And it's the value in the middle. So your starting value is P, or P hat, depending on how you want to express it. And it's either the average of those two, or finding out some way of finding out what the middle is. So you can certainly average those two, but you need to be halfway in the middle to get that value of 0.42, because that's going to start you off. All right, so from that, we can then work out, well, what are the various parts? You've got this margin of error part. You've got your P hat that you can work with. So we've got P hat, we've got a margin of error from the question, or as I said before, working your way through these particular steps to find them. I've lost the last one. And from there, we've got our formula, standard error formula. All right, again, pick up the correct one. You can plug in your values to find your standard error. Margin of error is Z times the standard error. We're after the confidence level. right? So to get to the confidence level, it's really asking ourselves, well, what's Z? How many standard deviations do you want me to go away? How confident do you want me to be? So it may not say find Z, but that's the solution pathway. You find Z, then you can go back to find out what the confidence level is. So find Z, 1.28. Again, you're thinking, you don't need to draw it. You're thinking about, what have I found? I've found a p-hat. I've found plus Z times the standard error. I've found minus Z times the standard error. This is your thought process in terms of the way you're building it up, because I'm going to want that particular area, and that area is, I'll actually draw this out a bit neater. Apologies for that scrappy work. It's got a nice bell curve happening. So we're centered on that value of 0.42. All right, we know our Z value, we want to head out 1.28 standard deviations either side. All right, so what does that give us in terms of a confidence level? How confident am I going plus 1.28 lots of the standard error, minus 1.28 lots of the standard error? All right, and that's going to be our inverse, sorry, our norm CDF, because we want 80% between those two values. Oh, sorry, we're finding 80%. I've gone a little bit backwards there. So we've got the normal CDF. We know our regions. We want to find the 80% confidence level. All right, that is it. Sorry, that last one got a little bit skewed as that slide went off the page, but that is it. So hopefully you guys got something out of that. As I said, I will upload the solutions and the blanks to the website, and I'll give you the link to that. And yeah, if you stay tuned and stay in touch, check in. We've gradually getting on board with the socials and that sort of stuff. So we'll have some extra material, and we're going to run some more formal lectures in the lead up to exams. So call it quits there, guys. So any questions, yeah, please get in touch. Otherwise, all the very best for the rest of the year and for your exams. And yeah, hopefully we'll touch base in the future. Thank you.